Welcome to today's webinar, Bridge Plate and Multi-Plate Applications and Case Histories, with Randy McDonald, Professional Engineer and Engineering Manager for Armtec, and Ron Prahitko, Professional Engineer, Senior Business Development Engineer with Armtec as well, in the Drainage Division. Without further ado, we're going to start with Randy McDonald.
Oh, that's great. Thanks, James. On behalf of Ron and myself, I'd like to thank everyone for joining today's webinar. This slide illustrates the two corrugated structural plate products we are highlighting today, multi-plate and bridge plate. Both are used to construct a variety of segmental steel plate structures, which when assembled on site will offer a wide range of shapes and sizes for buried infrastructure applications. The larger, deeper bridge plate corrugation profile expands the range of potential applications due to its increased stiffness and load resistance as compared to the shallower multi-plate corrugation. The agenda summarizes the topics that Ron and I will be covering. I'll start with a brief overview as to the origins and history of multi-plate and bridge plate, followed by the benefits of buried plate structures and available coating options. Specific to engineering and design, I'll elaborate on how our experience, knowledge, and customer service can be utilized to develop economical solutions through multi-plate or bridge plate applications. We have numerous case histories lined up to present that cover a wide range of applications. Within these case histories, end treatment options will be shown, along with photos of custom fittings designed to fit site conditions and or specific application requirements. The American Rolling Mill Company, or ARMCO, based in Middletown, Ohio, pioneered the development and introduction of heavy gauge corrugated plate that were factory punched, curved, and zinc coated after production in 1931. This enabled larger diameter drainage pipes to be bolted on site in comparison to regular CSP. Armco selected the trademark name of multi-plate at that time. As a footnote, Armco expanded into Canada around the same time frame as the introduction of multi-plate by purchasing the Canada Ingot Iron Company. At that time, Canada Ingot Iron had facilities in Guelph, Ontario, Sherbrooke, Winnipeg, Edmonton, Regina, Calgary, and Vancouver. The original multi-plate corrugation profile with a 6-inch pitch by a 1.5-inch corrugation depth eventually increased to a 2-inch corrugation depth by 1952. Today, the multi-plate profile remains at 6 by 2 or 152 by 51 in metric units in North America. The market demand for larger diameters and shapes other than round grew. By the 1960s, a variety of shapes were available, including arch, open-bottom spans up to 12 meters. In combination with large spans, deep bury applications were encountered. In 1975, a 15-meter span multi-plate superspan arch known as Vieux Comptoir was designed with custom straining footings, which proved the ability for the arch to support the 17 meters of overburden. In 1984, the world's largest multi-plate superspan arch was constructed in Ontario. It comprised of an 18-meter span open-bottom arch. Armtec introduced the larger bridge plate corrugation profile in 1999. Bridge plate arch structures can now exceed 18 meters in span. With enhanced section properties, bridge plate arches are able to match the same spans and larger without special features required by the multi-plate superspans. Manufacturing advances in the early 2000s enabled roll curving of bridge plate sections to relatively tight radii. This development enabled a new family of bridge plate box culvert structures to be introduced. Box shapes with a low rise-to-span ratio are ideal for low headroom open bottom applications, as can be seen in the photo on the right. The Armtec name evolved from the sale of Armco Canada Ltd. in the 1980s to Canadian interests. The Canada Ingot Iron Company was founded in Guelph, Ontario in 1908 and had been associated with Armco in the early years of culvert manufacturing. They were eventually acquired by Armco over 70 years ago. In 1930, Armco, as the leader in steel culvert industry, published the first handbook of culvert and drainage practice, which is shown on this slide. Several editions and 84 years later, this handbook, now published by the Canadian Steel Pipe Institute in Canada, still remains a primary resource for designers for the solution of surface and subsurface drainage problems, as stated in the original handbook. Moving on into the benefits of plate structures. Segmental plate structure Segmental bolted plate construction enables unique geometries to pre-engineered and manufactured to precise tolerances in controlled factory conditions. The compactness of nested plates minimizes shipping volumes, which provides economical transportation to remote and international destinations. Individual plates, although typically too heavy to maneuver by hand, are easily and typically hoisted with light cranes, boom trucks, or excavators, equipment common to most road builders. Buried steel structures rely on support from an engineered soil envelope surrounding the shell to maintain their shape, while also shedding load into the soil envelope. The complex soil-steel interaction enables the buried shell to resist large surface loads by dispersing loads through the soil envelope. The net result is buried structures can be economically designed with significant reserve capacity for overload conditions. The other benefit of soil steel structures is that roadway subgrades extend directly over top buried structures. This feature allows the asphalt pavement to extend over top the buried shell, eliminating the need for bridge decks. Coatings. Speak briefly about two coatings. Zinc is the basis of the protective coating known as hot-dip galvanizing. Zinc cathodically protects steel by sacrificing itself to protect the underlying base steel from corrosion. Even if the coating were damaged, zinc's sacrificial action will protect the exposed steel up to a quarter-inch away from the damage. The tightly adhered coating, with a bond strength of around 3,600 psi or 25 MPa, has an excellent abrasion-resistant properties, as the intermetallic layers are harder than the base steel. The weight of zinc that is possible to adhere to a structural element is a function of that material's thickness, its chemical makeup, and dipping time in zinc kettle. The required zinc thicknesses for multiplate and bridge plate structures is defined in CSAG 401. The Canadian material stands for corrugated steel pipe products, which is shown in this table on the slide. The past decade has introduced polymer coatings for buried plate structures as an alternative coating. Armtec's trade name for polymer coating is Stratacat. Polymer coatings are a second barrier coating applied for further protection of buried elements. Comprehensive research and testing recognizes that polymer barrier coatings broaden the allowable range of environmental parameters that are known to negatively influence the estimated material service life of buried steel structures. A four-step polymer coating process entails a diligent surface preparation to eliminate mill scale, followed by an 8-stage pretreatment wash of the base steel to ensure optimum adhesion of each subsequent coating layer. This is followed by the application of a zinc-rich base layer to a thickness of 1.5 mils per side. The copolymer is spray applied to individual plates, which then pass through ovens to complete the bonding to the zinc base metal. A comprehensive technical paper entitled The Performance Guideline for Buried Steel Structures is available as a free download from the Corrugated Steel Pipe Institute website. This guide is also supported by a white paper detailing the science behind this document. Engineering experience and design services. Armtec's engineering experience and design services extend back to the origins of multiplate. As a result of this, there are numerous applications whereby our expertise provided a practical and economical solution. For this wind farm site, a creek crossing was completed with an 8-meter span bridge plate arch. The overload design criteria, however, was a 440-ton crane, which exerted a ground pressure of 150 kPa as it traveled along the road at a very slow speed. This photo was taken during the first stage of backfilling a multiplate superspan arch mine portal. Upon completion, the multiplate arch supported a maximum overburden depth of 20.5 meters at the mine face. Knowledge of the mechanics of the behavior of buried metal structures continues to grow at an accelerated rate with new research initiatives and the availability of sophisticated finite element modeling programs. There are various commercial finite element programs available today. The rigorous method of analyzing buried multiplate and bridge plate structures is accomplished using finite element tools. These programs model both the steel shell and the backfill envelope. This is especially helpful whenever applications require non-standard live loads such as a mine or construction traffic, as well as structures that are beyond the physical size constraints of current bridge codes. This slide displays the bending moment diagram for an 11-meter span bridge plate box culvert supporting an overburden and highway live load. Similarly, for the same structure, this slide provides the total vertical stress experience in the soil envelope surrounding the box culvert. I've summarized the technical support Armtec can provide over the next two slides. Armtec brings to the table solutions for buried structure applications that may have been overlooked or not considered viable for other reasons. Armtec technical representatives track projects from conception to completion. Support continues beyond receipt of an order as our application specialists travel to job sites to share their knowledge of best practices for buried structure construction. Shape and fitting options. Multi-plate and bridge plate structures are available in many shapes. Individual plates are factory curved, thus the potential geometrical configurations are numerous. In addition to the 9 shapes identified, these photos illustrate 2 additional geometries. The top structure is a pear-shaped multi-plate on a footing, whereas the bottom photo is a box culvert framed by a cast-in-place head wall and gabion wing walls. Sites can demand alignments other than a straight run. The next 4 slides illustrate various custom fittings available for a multi-plate and bridge plate projects. All assemblies are plant fabricated, then erected prior to galvanizing to ensure a proper fit up in the field. They are then disassembled into sub-assemblies that are compact enough to ship by regular truck freight without the need for wide load permits. This Saskatchewan application required a fabricated T-connection for a bridge plate arch. This Alberta application required a 36-degree horizontal elbow for a 16-meter span bridge plate arch. This application required an 8-degree vertical elbow for a 7-meter span bridge plate mine portal in the Northwest Territories. Lastly, this Manitoba application requires laterals framing into a bridge plate arch mine portal. The laterals provide a safety zone should workers need to move out of the pathway of vehicular traffic traveling down the mine portal. End treatments. End treatments play an important role in buried structures. For watercourse crossings, a properly designed end treatment can improve the hydraulics, provide structural resistance to hydraulic forces, eliminate piping or seepage through the backfill envelope, reinforce the structure while retaining the roadway embankment. End treatments determine the length of the structure. Selection of the proper end treatment needs to address these variables and more. Also, end treatments basically frame the typically highly visible end views of the structure. Their importance cannot be overlooked. Several end treatment options follow. For this New Brunswick application, galvanized bridge plate head walls and galvanized Armtec bin wall wing walls frame a bridge plate arch. Tension rods extend through the backfill in order to tie the opposing head walls together for structural stability. For this Quebec application, Armtec light gauge galvanized sheet piling was employed. The sheet piling extends below the multi-plate horizontal ellipse invert to eliminate scour and undermining concerns. A BC Forestry Road application utilizes welded 4x4 wire forms for the head walls and wing walls. The exposed front face is lined with an Armtec geotextile to retain fine materials. Wire forms are easily adapted to fit the curvature of multi-plate and bridge plate arch structures. Step bevels are an economical end treatment option for this Newfoundland highway underpass. The cut side plates of the bridge plate arch act as retaining walls and are designed as such. The sloping cast-in-place concrete collars provide the stability for the bevel cut plates. A skew end is defined whenever the ends are cut at an angle other than 90 degrees to the longitudinal alignment of the structure. This typically occurs when the alignment of the structure is not square or 90 degrees to the roadway. A skew cut across multi-plate or bridge plate corrugations will result in the scallop corrugation profile being revealed as seen in this photo of a BC application. MSC head walls, utilizing either precast panels or cast-in-place panels, complement these bridge plate arches, both located in Alberta. Into some applications and case histories. These multi-plate round pipes. An earthen berm causeway across the Sims River in Labrador hosts 3 5-meter diameter multi-plate pipes to manage the river flows. For this East Coast application, a 6-meter span bridge plate box culvert utilizes a full multi-plate invert. This eliminates the need for cast-in-place or precast concrete footings. Arches on footings spanning waterways are common applications for multi-plate and bridge plate arches. Bridge plate capable of wider spans than multi-plate can also support deep berries as noted in this Newfoundland highway application. Armtec is responsible for many innovations in deep corrugated structural plate and exports product around the world. This annual overpass utilizes triple bridge plate arches over a multi-lane divided highway and service road for this European site. The divided highway overpass is comprised of twin 18-meter span bridge plate arches mounted on a 1.5-meter high concrete crash wall, plus a third 12-meter span bridge plate arch for a local service road. This 10.3-meter span bridge plate arch provides a 2-lane service road access under Highway 50 in Quebec. A cast-in-place head wall provides secure end treatment. Typical clearance requirements for 2-lane roadways are accommodated in this 12-meter span bridge plate arch. 1.5 to 1 step bevels follow the embankment side slopes. These identical structures provide an interchange at the Trans-Canada Highway in the Long Harbour Road intersection for the photo on the left. The same bridge plate arch accommodates a great separation between the Conception Bay North bypass road and a local road. Both these applications are in Newfoundland. The same bridge plate arch accommodates grade separations at 3 sites on the Torbay Road bypass and local roads also in Newfoundland. Twin 9-meter diameter round bridge plates were constructed to enable railway traffic to cross the Armtec River in Labrador. With a 2-meter berry, the 8mm thick bridge plate shell supports the E90 railway live load. The head wall construction combined a cast-in-place portion extending to approximately 5 meters above the bridge plate invert, and a RICO MFC retaining wall extends to the finished grade. Structural plate steel arches are relatively lightweight when compared to concrete, but they won't actually float away as this image suggests. A major intersection of the future multi-lane highway and an active railway line necessitated subassembly of 15-meter span bridge plate arches in a staging area immediately adjacent to the tracks. During the assembly, when the train traffic was reduced, 3 sub-assembled bridge plate arch sections were hoisted and landed into the cast-in-place footings. The final configuration not shown here is a twin bridge plate arch built with precast MSC head walls and wing walls. Armtec's international sales group were instrumental in securing this project located in the UK. Buried steel structures provide numerous solutions for mining and oil or gas plant infrastructure applications. A 6.8-meter span bridge plate arch mine portal located at a mine in the Northwest Territories provides vehicular access down a 15% incline to the mine face. Shipped to the job site over winter ice roads, construction followed during the short summer months. 6 bridge plate arch structures ranging in span from 7 to 12 meters were constructed to function as utilidors at this New Brunswick LNG facility. A 15-meter span bridge plate arch was constructed for a copper mine in British Columbia. The design haul truck was a 1 million pound CAT 797 vehicle. The bridge plate arch, capable of supporting extreme live loads as illustrated in this case history, provides an economical overpass solution. Block head walls completed the end treatment on this application. This 9-meter span bridge plate ellipse was built for the 2010 Vancouver Winter Olympics. To accommodate the women's giant slalom race at Whistler Mountain, a skier underpass was built under the racing course. Unbalanced, permanent gravity live loads provide unique design challenges, which were modeled in a rigorous finite element analysis and design. Day skiers can now pass safely under the racing course. I'll now pass the presentation over to Ron P.
Before I get started, I just wanted to remind everyone today that both of our products here, multi-plate and bridge plate, are supplied to meet all the specs and requirements of the CSA. Randy mentioned this earlier, G401 corrugated steel pipe products standard is for the manufacture, fabrication, and inspection of our bridge plate and multi-plate products, as well as all of our corrugated steel pipe products. And if you're interested in obtaining a copy, please visit the CSPI.ca, which is the Corrugated Steel Pipe Institute, and you can obtain a copy for yourself. So I wanted to get started here just by introducing some case studies. The first one here is a multi-plate arch which was installed in a very remote community in northern Saskatchewan. This particular one, the bridge was replaced, the footings were inspected at the abutment and were deemed to be in good condition and reusable. So the foundation for that had already been in place, and the arch was selected based on the span of between those two footings. In addition, Armtec designed and supplied a MSE wall with a geocell fascia component to this to keep the structure as short as possible for obvious reasons at this site. So here's a depiction or illustration of the cross-section of the MSE wall with the GeoWeb. GeoWeb is collapsible, and then when expanded is infilled with the granular material used for the structural component. In addition, the wall itself is constructed concurrently at the same time as the backfilling of the multi-plate structure. Here's a photo showing the backfilling procedure. It's a very simple procedure. Often in these cases with multi-plates and these types of MSE walls, it's very repetitive. And for this particular site, I wanted to make sure everyone knew that all the materials, because of the remoteness of the site, Uranium City is located in northern Saskatchewan near the border of Northwest Territories. All the materials were shipped on one truckload over the winter road, which made it for the economies a very economical structure for a replacement in these communities. Highway culverts used in many parts of Canada are well accepted. Here's an example of a highway culvert installed in northern Alberta near Valley View, DeBolt Creek. It's approximately a 5-meter diameter, under fairly deep fill, about 5 to 6 meters, and the wall thickness of this varied with the depth of cover just to provide some more economies for this structure. You also note some excellent end treatment was designed and incorporated into these culverts, which is an investment definitely worthwhile and recommended for culverts in hydraulic situations. Is that you see beveled end treatments, you see cast-in-place concrete collars. The invert of this structure is founded well below the natural stream bed, and the ends are protected with rock riprap, as well as many other erosion control measures that you see that have been adopted here post-construction. So there's a number of different considerations here for culvert end treatments, especially in hydraulic situations, and I've traveled all over Canada and seen many culverts in distress, and by far most of these culverts are a result of a lack of or very poor end treatments. Here's an example of some very good end treatments that have been incorporated on the end of these two corrugated steel pipes. These features here all counteract the large hydraulic forces that are encountered at both the inlet and outlets of structures. Cast-in-place collars protect and strengthen the beveled ends. The beveled ends themselves are certainly improve the hydraulic efficiency at the inlets, as well as there's invert is located well below the stream bed, and also there is a cutoff wall to protect against piping or erosion at the inlet and outlets. So typically with multi-plates, there is plate assembly, and in every province in Canada there are usually contractors that specialize in this and become a bit of a craft. They quickly can assemble culverts, and they use a variety of techniques, and to assemble these they have perfected this and do a lot of pre-assembly of the plates or arcs off to the side before bringing them down into final assembly, which really quickens the amount of time to assemble these structures in place. Here is a unique application of a multi-plate horizontal ellipse. Horizontal ellipses are very popular for obvious reasons. They're lower profile and certainly can provide a lot of room. This is a wildlife underpass, and there's a number of these horizontal ellipses installed under the Trans-Canada Highway within Banff National Park to allow the wildlife to pass under the highway. You'll see a sand bed in place here. The biologists actually track the wildlife that cross by looking at their footprints or hoof prints. And these structures do work for that reason. They've been successfully employed on many parts of the Trans-Canada Highway. This is a pedestrian underpass, very unique shape, and it lends itself ideally to pedestrian underpasses. It is a 4-radius shape. As you can see here, there's 2 examples, one in Newfoundland, another one in Calgary. These are standard structure sizes and can capture a lot of headroom for pedestrians as well as bicyclists or recreation traffic. Wanted to show you this very unique application of multi-plate. This is for a new potash mine in Esterhazy, Saskatchewan. The designers came to Armtec looking for a possible solution to bring fresh air down into this new potash mine through these ventilation plenums. And you can see here a fully pre-assembled 4.5 meter diameter multi-plate that is being hoisted into its final position. 2 of these ventilation plenums were supplied to this potash mine to bring fresh air down into both the service and production shafts of the mine. Here's another photo just showing the details or possible details that were incorporated here for connection to the concrete wall at the bottom of the slope. This was installed on a 30-degree slope, so it obviously had to be pre-assembled beforehand. Here's the ventilation plenums emerging from the ground, and a variety of different appurtenances were connected to it, air handling equipment and fans to push the fresh air down into the new mine shaft. Randy mentioned earlier that seam sealant was a way for sealing these. Full seam sealant was incorporated at all of the joints here, as well as the StrataCat coating. Potash, by its very nature, is a very corrosive type of material for galvanized steel, and the designers incorporated or specified StrataCat coating for this particular application. Randy showed this slide earlier. With segmental plate structures like multi-plate, you can see on the photo here on the right a multi-plate pipe arch where the invert has actually been supplied with StrataCat coating and the top arc in our standard heavy galvanized coating. Most of the wear, corrosion, and abrasion occurs at these invert plates, so there's the ability to do this on these segmental plate structures. Conveyor covers are excellent example for multi-plate structures here for aggregate stockpiles. Here you can see from the inside here, this is a multi-plate vertical ellipse where hopper openings were designed and supplied by Armtec to capture or to allow aggregate to come through the roof of the structure into the conveyor system. Armtec supplied and designed all of those hopper openings. We definitely need to know aggregate piles, maximum and minimum heights for these design purposes. Another multi-plate structure here in British Columbia, Dick's Booth. This is a StrataCat coated multi-plate and incorporates another one of our head wall systems, the Armtec lock and load retaining walls, and more information is available from your local Armtec rep if you want to find out more about these end treatment options. I want to give you a few case studies of some bridge plates. Randy showed this slide earlier. This is of bridge plate low profile arches for animal overpasses in Banff National Park, allowing wildlife to cross over the Trans-Canada Highway. Twin structures, one for each of the east and westbound lanes. Structures were designed, the shape was specifically designed to capture the clearance box for this particular crossing, which was 12.4 meters in span by 5.6 meters in rise. In addition, it allowed for pedestrian access along both sides of the structure. Just another view of the end treatment. In this case, these were reinforced earth panels at the ends of the structure. Sask Highways have installed a number of these structures. This is a fairly remote location here, Highway 905, on the only highway up to uranium mines in northern Saskatchewan. Armtec's designed and supplied 3 of these low-profile arches, complete with wire mesh MSC head walls. Typically, all of these structures are pre-assembled. In this case, the assembler pre-assembled the full ring off to the side before lifting these in. Each structure was about 15 meters in length, and the pre-assembled rings were assembled into the cast-in-place footings in 2 days before backfilling was started. Here's a illustration of the welded wire mesh MSC wall showing reinforced zone. These types of systems work very well with the bridge plate systems because the same type of material is utilized, and backfilling and installation occurs concurrently with the backfilling of the multi-plate structure. As showed in this photo here, you can see the geogrid is laid out before another layer of granular material is placed and compacted in lifts, and we have an inspector on site for this particular job that ensured that the lifts were placed properly and compacted to the specified density on our drawings. Multi-plates or bridge plates are used for resource utility crossings. Here's an example of a box culvert, 8-meter span used in Fort McMurray to cross over an existing utility line. Again, you can see the use of MSC walls. Very important at these sites here to minimize the amount of time to do a lot of pre-assembly, and this is very common in many parts of the West, including Alberta and north. Here you can see a number of rings have been pre-assembled and ready for placement, which minimizes the amount of site time work. Another example here of a project with a total steel solution utilizing a bridge plate box and sheeting head walls with tiebacks. A remote location here, so this was proved to be an ideal solution for this project, which I believe is in a resource road in British Columbia. Heavy mine road crossings are an ideal application for deep corrugated or bridge plate products. This particular high-profile arch crosses under a heavy mine road, a heavy haul mine road. The high-profile arch was selected to capture a clearance box, and a 13-meter span by 10-meter rise structure was selected. As you can see there, the live load design truck was twin or 2 Cat 797 mine trucks that were fully loaded, crossing over the structure at the same time. So here you can see in this photo the structure has been fully assembled here. This was done by actually Armtec's erection crew up in the Fort McMurray area, and you also see some deep corrugated ribs that added to the structure here because of the very high loads, live loads that were required to be resisted. This is a unique situation here where the owner requested a structure that a crossing where you didn't even know you were traveling over a bridge or a crossing. This one incorporated a bevel end treatment with a cast-in-place collar. The bevel end conformed to the embankment slope. And then, as you can see on this slide here, mission accomplished. You don't even know you're traveling over a bridge, and this was a requirement for this particular crossing. Going back to Saskatchewan here, I wanted to show you this Garden River crossing, which was a 12-meter span, low-profile arch. Looks very similar to many of the other projects I showed you. However, the contractor came to us, and as the consultant had designed cast-in-place spread footings, wanted to minimize the amount of time within the excavation itself, and proposed a precast footing, which we went back to our designers and came up with a design. It was accepted by the consultants and owner, and it really assisted the contractor in minimizing the amount of time he had opened up the hole here and was diverting water around the site. Of course, you can also see that a lot of the pre-assembly work of the plates was done, which again minimized the amount of time that the contractor was in this excavation. For those of you listening in Maple in Saskatchewan, you may remember back in 2010, Trans-Canada Highway washed out after a severe rain event. This photo here you see was taken actually literally minutes before the highway washed out, resulting in essentially a real disaster and diverting traffic around the site here for many, many kilometers. It was a real inconvenience to the public. A representative in Saskatchewan was approached for an option, and a bridge plate arch, 11-meter span, was proposed, and it was stage constructed, and these structures are very easily stage constructed. This was done in the spring of, or the fall of 2011. This was the final stage here. It was the first stage was constructed earlier in the fall of 2010. I know we have just a few minutes left here, and I just wanted to just show you a couple of slides here. Many of you have heard about the devastating floods in southern Alberta last year, and I was fortunate enough to do a lot of traveling after the flood to evaluate the number of the culvert and bridge structures that were subjected to this flood. And two things I learned. One was it was a devastating flood affecting many, many families and homes and causing much damage to our infrastructure. And the second thing I learned was end treatments are not an option. The structures that performed well during these very high flow events had properly designed and installed end treatments. As you know, many of the designers are aware that there's many different types of forces that need to be accommodated at the inlet and outlets of culverts. And these include uplift, hydraulic uplift, erosion, and piping. One particular structure that I inspected after the flood was right in Canmore, Alberta at Cougar Creek. In the top of this photo, you can see the Trans-Canada Highway, but near the bottom there is a culvert that managed to survive this very, very large flood event. Here is the culvert actually under the flood conditions. This is normally a much narrower stream course, but during the flood event, which occurred at the same time as the melt in the mountains with these rainfall events, this particular site became a raging torrent of boulders and debris. And this was the structure post-flood. It's approximately a 10-meter span horizontal ellipse. Here's the inlet condition, and the designers of this structure certainly knew all about the traits of this stream and what the potential flows could do to this crossing, and they incorporated a number of different features to handle these types of flow events. As you can see, an excellent head wall and wing wall system was incorporated. Some of the locals I heard wished that those head walls and wing walls had extended much further. The structure was actually in somewhat danger of being washed out, so it had to be helped along with some heavy equipment to save it from being washed out. But there's also some other features, such as a sacrificial steel plate that we found post-flood that was incorporated at the inlet to protect against all of the abrasion and rock debris that had accumulated. There was also a concrete paved invert. The structure itself, after 30 years, was installed in 1982, was in actually terrific condition and withstood a number of these flood events. If anyone's interested, I've co-wrote a paper, and it's available at the Corrugated Steel Pipe Institute, their website. They have an article in there called, a newsletter called After the Flood, or I'm sorry, in the trenches. That's all I have for slides, and I think we're running out of time, so I'll turn it over to you, James, and see if there's any questions or what we want to take it from here.
Can you comment on minimum versus maximum overburden and the issues to consider in each scenario?
Sure. Minimum overburden is typically dictated by the Canadian Highway Bridge Code, which is S606. And just for the callers, just for designers on the line, the latest supplement was supplement number 3, and it was issued in March of 2013, a year ago. And there were some modifications to Section 7, which deals with buried structures. So I'd recommend you have a look at that if you don't have it. That bridge code for Canadian applications lists the minimum cover requirements for buried structures. Maximum cover is determined through an analysis of the actual application, and it is strongly influenced by the depth of the bury as well as the density of the backfill that's being considered.
How does the cost compare to concrete culverts?
Typically, buried steel structures come in at are more economical. There may be cases where that's not true, but the majority of cases, I think, would have to say that the majority of cases, when you're into a large span arch structure, there's no question steel would be more economical, as concrete may not even be able to accommodate some of the loading conditions that we encounter with steel structures.
What is the average life cycle for buried steel structures?
Well, typically the Canadian Bridge Code stipulates a 75-year design service life, and with the proper selection of coatings today, galvanizing, there are a couple of thickness weights of galvanizing that can be incorporated, but also with polymer coating, and 75-year is easily attainable.
Is there a long-term difference of steel arches versus concrete in terms of durability or longevity of the structure?
Design service life is truly tied to the environmental parameters the arches are subject to, whether they're steel or concrete. You know, I have to say that they're going to provide very similar service lives if or when the proper coating is selected for the steel. And similarly, you know, there are features you can add to concrete structures as well. So I don't think there would be any significant difference when properly addressed at the design phase.
What is the longest span ever done by a single steel arch?
I believe it's about 22 meters or 21 meters.
What if the plate gets dented during construction? Do you have recommended tolerances for using as is versus replacement?
Plates can be replaced. New plates can be supplied and shipped to site. But yeah, there are tolerances that are typically listed on drawings, on the installation drawings that are provided, which would suggest which is one way to help evaluate the situation. The advantages of steel structures is they are flexible, and localized damages to plates may not even have any large impact on the stability of the arch or the long-term performance of it. But it does have to be evaluated to ensure that the plate didn't go into reverse curvature, which of course would necessitate replacement. But very localized plate deformation to plates are readily tolerated by flexible steel structures in general.
Here's a good one. Is there any special hardware used for Stratacat coated plates on the side bolts?
Yeah, on Stratacat structures, we utilize our standard galvanized bolts. We haven't, as of yet, a Stratacat or polymer-coated bolt hasn't been developed. However, in most situations, it hasn't proved to be an issue. The bolt itself is a very heavy and thick component of it, and usually is not a limiting factor in the design life of the structures that have been StrataCAT coded.
Is it possible to extend existing multi-plate structures by coupling new sections, i.e. for a pedestrian underpass where the highway is being widened?
Yeah, actually, multi-plate lends itself very well to be for future extensions as well. Certainly, we need to know a little bit about the existing structure, and if the original drawings are still existing, then that would really simplify it. We could very easily come up with an extension and plates to do that. In addition, there's always you can always contact a local Armtec rep that would do a site visit as well, just to ensure that it was done properly and the extension was could be fitted properly in the field.
There's a question about chemical resistance. Are there chemical resistant charts available for different types of coatings?
We have a Randy referred to it, the technical bulletin on coating selection and guidelines for the various coatings for structural plate. Certainly, if there is potential for chemicals that are not normally seen in storm water or streams, then encountering that, one may want to consider just the use of specifying a StrataCAT coating product. StrataCAT being a polymer coating and is highly resistant to all types of chemicals and corrosion.
Thanks again for everyone who attended. You can always find more information on Armtec webinars at armtec.com/webinars or on the News and Events tab if you're on the site already. Please join us on social media. You'll find us on all the usual channels: Facebook, Twitter, LinkedIn. YouTube has a lot of technical content as well as previous webinars recorded there. And in terms of reaching Randy and Ron today, here are their emails. Those will also be included in the follow-up email and the customer survey. As well, you can find your local rep by going to armtec.com/contact-us. And of course, you'll find lots of information on the Armtec site.